All right, the thing has been hit. Hey guys, what's going on? I am joined today with the creator of virtual physics and co-founder of the Physics Monastery, Echelon Azha. Say hi to the folks, Echelon.
Hi, all. This will be a great demo, and especially this is geared towards mostly programmers.
Well,
So
we kind of gave it away when we said it's like program with virtual physics. So, we kind of spilt the beans right there. And we had done a couple of teasers over the past few days on this about what is actually going on. And after some guidance before the stream, I at least have this stuff installed and a terminal that I can try to start doing some stuff and things. But hopefully, Echelon will be able to help guide us through what we can actually do with virtual physics. So, sir, would you like to take it away?
sure. Actually, the first thing I want to describe is what this is. I created a separate video called the Universal Library that is more whiteboarding and goes over some of the theories more in depth. This will be a little bit more practical, going through the code, explaining kind of what's there and giving the idea. And um, my number one goal is to describe what this is and what this isn't, and what this is very good for and what you probably shouldn't use it for at all. Um, so starting with what this is, and the goal of this project was to basically, let me back up a little. In general, building software libraries is like trying to build the ultimate Lego set. And one of the problems with building the ultimate Lego set is they're kind of man-made parts. So in version 1, if you want to build a castle and I have a Lego set, and I'm a hero in version 1 because you can build the castle, you can build the walls, you can build the bridge. It's a perfect Lego set with 10 interchangeable pieces. And version 1, I'm a hero. Version 2, somebody comes along and says, well, I want to build a boat. And I have a perfect Lego set with a rope, a rudder, a sail. I start getting some exceptions, and version 2 is not so bad, but there are some exceptions. The sail doesn't quite fit with the Legos. Not too bad. Version 3, somebody wants to build a car and have a perfect Lego set with a rope, a rudder, a sail, a windshield, tires, and so on. After a while, you end up with more exceptions than rule, and you find out that your ultimate Lego set doesn't handle a lot of conditions, shapes. It doesn't really have the parts that you can build everything you need. So I started looking at the laws of physics, and we have protons, neutrons, electrons, gravity, and so on, and we can build everything in the universe with these parts. In theory, we should be able to build everything in the virtual world with these parts. So the first challenge is first trying to build something authentic, trying to build something that simulates the patterns of protons, neutrons, electrons, and so on, get it as authentic as we could. And then what becomes really difficult is, how do you build a program with neutrons and protons? What is gravity in a program? What do electrons do? So it's a matter of interpretation. So getting those interpretations exactly right. What we're doing is we're interpreting the laws of physics, taking the patterns out and applying it to programming, and hoping we have a really good interpretation. And over 22 years of scrapping it and working on it for about 4 or 5 years, scrapping it again, starting over. Eventually I came up with a really good, very close interpretation to the laws of physics, and using the patterns to build programs. So that's what you're looking at. And that's what we will be looking at. I'll be going through some of the code to give some ideas. And the advantage of this approach is and it's been uncanny over the years. Many times I just wanted to give up and say that we can't even do this. This is a dumb idea. But I noticed the more authentic the library came to the laws of physics, the more superpowers it just seemed to have. It was always amazing. Like, wow, this is built in. I can use this for that and this for that. And you'll see as we walk through it, this has several superpowers. One of the big things is the code is very, very tiny. It has no dependencies. The laws of physics are the laws of physics. It shouldn't depend on anything. And so it's a tiny amount of code. So right with that, you can kind of say that virtual physics is incompatible with everything that's been built so far. We're really starting over using virtual physics as the core laws of physics. It's kind of searching for the unified field theory of programming. That is really a good way to put it. If, for people who are familiar with the world of physics, Einstein searched for the unified field theory. This is looking for the unified field theory of programming, some universal way of programming where we can become software engineers in the true sense of the word. The chemical engineers are engineers because they're governed by the laws of physics, mechanical engineers, nuclear engineers, and so on. They're all governed by the laws of physics. We are not. The word software engineer is kind of suspect. What does that really mean? Well, with virtual physics, we become engineers, and this is the goal, where we're actually building on the laws and patterns in physics to build everything. And there's some interesting things that come out, which I'll speak on later. The way we approach software development, it brings out some interesting things, but it also makes it very incompatible to everything we've done so far. So I'm in the process. I'm working on a server, some website tools. Everything has to be rebuilt from scratch. So anyone who's interested in this project is certainly welcome to find out more and join us. And so let me begin with a quick description of the code, what's here and how it's organized. One thing you'll notice, I have applications where I have test cases, and even my tests, my goal is to have multiple languages. Definitely TypeScript and Java are next in line. Picking any particular testing framework means it probably won't work with the others. Like, I do TypeScript, JUnit won't work, and so on. So anyone who's interested in writing a new testing framework that would be cross-platform, built based on the laws of physics in virtual physics, that definitely there's a place. But I've made some test cases.
Echelon, I'm sorry to interject. Can we rewind for maybe just 2 or 3 minutes and kind of explain the part? I understand, when you kind of explained to me, you were like, it's like, I don't feel like I'm an actual software engineer, even though that's what my business cards say and everything, because you felt like, well, I was doing programming, but you didn't feel like you were an actual engineer. So kind of maybe you could kind of reiterate some of the discussions we've had before, but just quickly, about essentially for a noob like me, just a dude on the internet, basically why we've gone faster processors, more RAM, and blazing fast internet speeds, but the internet as a whole really doesn't seem a lot faster than it was 10 or so years ago. I feel like that's something I think a lot of people notice, and we're not really sure why. But I think your quick description might help people out.
Yeah. Let's go back to the reason why they call us software engineers to begin with. And I think that title came about because people want the assurances from software developers that what we design won't fall down. People who design bridges are engineers, and they have math to prove that this bridge will stand, and they can give certain assurances that we can't give. So they call us software engineers, but we're really not engineering anything in any sense of the word, other than I think we're closer to architects, and we to the sense the assurances we can build that we can give when we build software is kind of like if we were using music theory. You can play a note that's out of key and bend the note and it sounds great, you go with it. We build our own universe. We use a Mac, we pick Kotlin, we use this framework, that becomes our universe, and the laws are very inconsistent. So the goal is to achieve true software engineering, where we have a consistent framework that everything is built on top of, just like real engineers have. And
real physics, just coherent process of physics and stuff. Because I mean, if that's what we're going to claim, I mean, we should try to be consistent. If there's inconsistencies, I mean, that could always be worked out, and just be honest with people. That's all.
Yeah, and there's one universe and one set of laws, and if we're following that, there should only be one base library that you can build everything out of. And if you can't build everything out of it, then maybe this is not achieving its goal. But so far, I've built 2D graphics, I've written servers, I've done parsers, like I've written client and server side, written custom B-tree type databases, and all with this tiny core of base classes. Like if you look like here on the screen, my dependencies, I'm depending on Kotlin, their reflection class, and there's some date time. There's no other dependencies mixed in. And that's to do everything that you see. The core library has 370 files, but actually I might be using probably 200 or 250 of them. And
No. Just for people's context and stuff like that. You see 375 files. I'm like, I could plausibly count that high. In general, when you look at like real world projects, like you've actually not giving any specific details that you're not allowed to, but just in general, some of the libraries you've seen are much larger than this. Could you give folks maybe an idea of the scale of a lot of like libraries nowadays?
Yeah, on average, like if you're creating a React app or an Angular app, you could easily have 1,000 node dependencies in your list. The same thing when you're, developing on the server side, thank God for Maven, because without something like Maven that, imports all of your dependencies, it would be too many to we wouldn't even be able to build our apps without Maven and being able to, have a package builder that builds it for us. So there's actually fewer files in here than the average product that you're building has whole dependencies with thousands of lines of code each, sometimes tens of thousands.
I remember the first time you're just going through some random stuff. It's like, there's like a million things in this library. I'm like, a million? How many do you have? Like 300-400.
Yeah, of just files. And so this is very tiny. And one of the things that I've noticed over the years, if you go back to 1995 and you have a team of developers, 6 or 8 developers, and you say I have good news and bad news. The good news is we're going to build a really cool website. It's kind of rudimentary for the technology back there. And we're going to do something really cool, whatever it is. And they'll be great, excited. When do we start? And say, well, there's some bad news I got to give you. The bad news is you're not allowed to use any open source. You just got to use the compiler and the basic set of tools. Good luck. And they'd look at me like I was crazy. Open source? What's that? I never heard of it. And why would anyone give away software for free? And they'd get to work and they'd build something amazing. 25 years or so later, you have the same, another team, and you say, I have good news, even better news, and a little bad news. And, okay, well, the good news is we're going to build something really cool. We're going to build a website, and okay, great. The even better news is your processors are 1 million times faster than they were 25 years ago. You have 1 million times more memory. Networks are 1 million times faster than they ever were. Great. Like, when do we get started? What's the bad news? The bad news is you're not allowed to use any open source. The team would stare like, a deer in the headlights and say, well, then it can't be built. And we've kind of lost our way. And we want to say that the stuff we're building today is much more complicated than it was back then. But I'm not really finding it. We've made it more complicated by the total number of dependencies that we need. And a lot of the work that we're doing, we have a very brittle set of dependencies, several hundred packages that we're including. And when one of them changes, it requires a rippling change somewhere else and somewhere else. And a lot of the work that we do as developers in upgrading this stuff is trying to maintain dependencies. And virtual physics kind of starts from scratch and gives us a very tiny set of files that we build on top of. My server, it's a WebSocket server. It's not ready to be released yet, but it's in a couple of hundred files for the whole server. and it's built on top of virtual physics. And
well, isn't it like under like 2 megabytes or something like that for the server?
yeah, I think it was 1.1 megabytes actually to
Yeah.
start up, and can handle multiple users. And
Now, how does that compare to some of the other servers you see that maybe like a large company is using? I realize there's a scalability thing there, but just as an underlying framework.
oh, probably a million lines of code. Like, most servers are very complex. One thing, this won't have to be that complex. Like, now you can say we're comparing apples and oranges. Like, a custom server to do something custom doesn't support everything a general purpose server has to support every possible thing, like JSON and XML and you name it. Yes, that's true, but this doesn't need JSON or XML for messaging because it's built in. And you'll see some of that.
Can I give a quick analogy? Because, and again, correct me if I completely butcher this, but it kind of reminds me of like Monty Python and the Holy Grail, and Lancelot's visiting the king, and King's like, they said you couldn't build a castle in a swamp, but I built it anyway. But sank into the swamp. So I built a second castle. That one burned down, fell over, and then sank into the swamp. But the third castle stood. I'm like, well, you already sacrificed 2 whole castles to basically like get your like foundation there. So like there's enough stuff there, and then you build it. I'm like, it kind of sounds like we built things, and rather than going back and again, a lot of this is probably just because of the incentive system. Oh, just get this done. We don't need to spend the extra time there. We already have something. The computers are getting faster. The internet's getting faster, yada, yada. And we can build and build. And then once you hit the breaking point of Moore's law, it's like, well, we seem to be developing chips on like literally atom per atom now. So we kind of can't get any smaller with this size. And the internet speeds are fast, but they're already dealing with this and everything. So it's like, something's got to give. So that's why I think this is the time in history where a lot of folks would be more open to this. And the greatest objection to overcome for this would be like, well, everything else is written somewhere else. It's like, well, how could we spend all the time and resources to get this stuff written? I'm like, if this thing is simple enough, I mean, we have our LLM friends that at least have helped me and Thad, like actually like start learning to code with Python and stuff. And if this is a lot less complicated than Python, if it can start to learn this, a lot of that stuff right now, we have the scalability and the computational power to actually start to pump out. All I know is if you could solve the problem of live drawing, man, I think some of the folks from Google Stadia might be giving you a call. Just my opinion.
I think that's coming. And, with that intro, let me go through the code. And to give an idea what's here, you'll see like right at the top, there's asymmetrical code and symmetrical code. And
maximize this. Go on.
Okay, yeah. So what asymmetrical code is code that's not identical on every platform. An example. Let me see if, let's say we go to A bytes here, 2-byte array, 2-char array, and let me share. I haven't released this code, but it'll give you an idea. Like on the web, I also have asymmetric code and A bytes. But if you look at this code, there's a difference because Kotlin is not perfect and it doesn't run exactly the same on every platform. So the code that's asymmetrical, that is unique to the web, if you look at, let's say, 2-char array, I'm saying byte array, 2-char array, and that is valid Kotlin for running, through the JavaScript interpreter when it compiles to the interpreter. But if we look on the Java side, that if it's running in the JVM, 2-char array, I'm creating a string, doing, whatever we need for Java without going into the details, but it's different. So I created a separate interface, and well, in this case, it's not even an interface. It's a concrete class that has 2-char array, but it's selecting when I'm running on the JavaScript platform or the JVM. The JVM platform is using this one. On the JavaScript platform, it's using the other. There's not a lot of things that are asymmetrical. 90% of the code is symmetrical. It runs on every platform. Forget these bitmaps, that actually belongs in the server. I'm going to move that out.
So this is basically an effect of, because there are different systems and everything like that. So that happens to be a potential effect of basically just our operating environment, or
Yeah, because the virtual machines for JavaScript and Java have
Mhm.
slightly different capabilities. They're not identical, but
Right.
this asymmetrical library makes it identical. They're basically adhering to the same interface. Kind of like when you have a car with the steering wheel and stick shift and brakes and gas. That's the interface of the car. The actual car, one could be electric and one could be gas, but the way you interface to it is identical. So this
So it's like swapping out like an automatic transmission for like a manual or something like that. So it's basically how you're interfacing, and that's basically just how it's developed there.
Right. The actual implementation is different, but on top of all those subtle differences, I created an asymmetrical library, one that is necessary for Java, one that's necessary for JavaScript, and the symmetrical code runs on top of that.
Mm.
And there's very little asymmetrical code. Kotlin has a way of handling asymmetrical code with what is it called? Expect and actual. You have the expected behavior in the actual code. I didn't use that because my goal, there's not really a good equivalent of that in Java and TypeScript and other languages. So I wanted to write it in a way that not only runs in different environments, but can be easily translated into new languages. So,
So this is the point where I make the executive decision, and then I I do this one thing. Now, Echelon, I realize it shouldn't matter. Why don't you give the folks a little bit? I should have done this at the beginning. A little bit about your background in the programming industry, and that who is this random dude that's saying all these things? Like maybe just some of your background would help. Kind of just explain like how you kind of got to this point, and you're not just like some random dude. It's like, who did the heck did you pull into this stream? Because I've heard some very random folks. I've also happened to have Stephen Wolfram on this same show as well. But at the same time, it's like kind of give folks a little bit of background, because you remind me a lot of Stephen Wolfram, at least in some of the logic. So why don't we give you the floor and just explain to folks?
okay, well, I started just about 50 years ago on mainframes. I started in the day when I was doing some mainframe assembler and COBOL programming, and then the microcomputers came out, and I published some software packages in the 80s. C programming language. It kind of emulated the mainframe in the day because that's the only thing that you can actually do real work on. It was a terminal emulator that had 3270 behavior for C language programmers. And I demoed my work in a booth in Comdex, and it turns out it was the perfect product for nobody. The C programmers who had a Unix background, never used 3270 terminals, looked at it and said, wow, this library is amazing, but that 3270 terminal, that looks too much like a mainframe. Give us a call back when you get rid of the 3270 terminal and the mainframe behavior. And the mainframe programmers looked at it and they loved that part, but they said, this C programming language, give us a call back when you do it in COBOL. And
You precisely made half the people happy about half the thing.
Exactly. So it was the perfect product for nobody. And I kind of learned a lot of lessons from that. But it took me 4 years to write it. And, I've had a long history in my life of spending years working on things because I really am interested in programming. I love it. And, I got into doing a lot of C programming and C++ in the early 90s. And, I started with object-oriented programming, and I thought I was good at it until I worked on a team with Smalltalk programmers, and I learned a lot from them because they really understood objects, and I realized everything I did in C++ was probably wrong and wasn't the right approach, and I started over. So I've had even as I got into Java, I've always carried a little bit of a Smalltalk seed in the way I'm thinking. As we fast forward, I've worked on all kinds of servers and, worked on online banking and, 50 years of applications. But throughout the years, I've noticed we always have the greatest thing, the right way to do something. This is the greatest thing. and everyone buys into it. And then the next thing, 7 years later, nobody's doing it anymore and it's gone. And I bought into that. I drank the Kool-Aid many years, but after like 20, 30 years, it starts getting old. Like, this is not the latest, greatest thing. And I started seeing repetitions that we're making the same mistakes and doing some of the things similar that we did 20 years ago that didn't work. But unless you've been in the field long enough, you won't even know that we're going around in circles. And so it was back in 2002 that I really realized that none of these libraries or frameworks, including my own, are ever going to be right. We keep doing the same thing over and over again and doing it incorrectly. And that's when I started thinking, nature has all the patterns that we will ever need, highly optimized. And that's when I started pretty much down this journey. And there's been, over the last, I'd say 5 or 10 years, like, the industry has been moving towards functional programming and saying object-oriented programming is evil, and you don't want side effects, and the idea you should call a function should always return the same thing. If you have an object and it depends on state, then you're polluting your code, and that's evil. But the more I worked on virtual physics, the more I realized that state is everywhere in the universe. I can have a pen, and a big pen in my car in the winter, frozen solid, and that pen won't write. And I can leave it on my desk at home and it warms up, and only the temperature is different. It's a change in state and the pen does write. So functional programming tries to create a stateless universe that doesn't exist. And I decided that the universe has it right. State is everywhere, all the way down to the atom, to the protons. There's absolute everywhere has state. So the more we're on this quest to build virtual universes that are stateless, the more I found that we're heading in the wrong direction. There are places where it's useful, but to say that object-oriented programming and storing state is the wrong idea, that's one of the areas where I'm opposed to the functional approach. I believe that programming should have state everywhere. And if it does, and it's using the laws of physics and patterns in physics, then we're going about it the correct way, because that's the way the universe works. And it seems like the laws of physics are way ahead of us.
So can I just share something real quick? Because this reminds me of something I covered literally the other day. This is a paper from Professor Roy Kerr. He's the progenitor of the Kerr solution, basically the solution that's generally accepted in physics for rotating black holes, i.e., the only black holes we've observed to our understanding. And I don't want to. I literally named the video. Was it physicist who solved black holes destroy singularities? It's kind of a hyperbolic thing, but he's kind of savage in this paper. And one of the footnotes is fantastic. It reminded me exactly what you were just saying here. Here we go. What is it? Footnote 15. Astrophysicists may say, "What is the equation of state?" Question mark. This is still a work in progress for a neutron star, i.e., nobody actually knows what it is. But that's a very good question, because if everything has state, that maybe we're onto something there. So that's yeah. I just wanted to share that real quick. So
yeah, one thing also is that there's a lot of people, the philosophical question, are we virtual to begin with, our universe? There's one observation I've had from this. I haven't come to conclusion whether we're virtual or not, but I really realized that if I went to my program, if I wrote AI out of this program and asked the program, how did the universe begin? The AI would say, well, it must have begun with a big bang, because the program doesn't know anything that happened before it was born. It would only see the moment it started running as a big bang. And if you asked a running program, how big is the universe? A running program would say it's infinite, because it sees no end. There's no boundary, no end. So I just find it kind of an interesting little coincidence that a virtual world would come to the conclusion it began in a big bang and that the universe is infinite. So I've kind of used virtual physics to influence my philosophies on life because I see a lot of similarities between the virtual world and the real world, mainly because I've been doing this so long.
I was gonna say, if we're gonna claim that, well, the most effective mode of programming in reality is reality itself. I wouldn't say that's even a bold claim. That's just an inference and an observation that we have. It's like, what if reality held the secrets to doing things better? Sounds good to me.
Yeah, and on that note, let me walk through some of the code so we can see what it can do. So I've discussed the asymmetrical code. Hopefully we have very little of it. And the symmetrical code. I'm going to have a test app here and test physics. Let me start with testing radiation. An address emission. Let me just scroll down. What I'm doing is I'm writing little test cases to verify that whatever I did just worked. Right here, I'm creating an address row. And normally, like if I want to send this to another machine, let me put a breakpoint. Maybe I can just run it. Sometimes things become more concrete when you say, okay, I'm creating an address row, Bob on Main Street, New York, New York. So I create this address row. And normally, if I want to send this to another machine on a server, maybe like I'm running this in the browser and there's some microservice that's going to take the address record and do something with it. Well, in general, I often don't know what language, and don't care what language the server is written in. And even if it has this address record, I will serialize this into some kind of JSON string, some kind of JSON format, send it to the other side. I'll probably use, JSON or something to, or some utility that I download to convert my code into a JSON string, and then have some parsers on the other side that I downloaded to parse it. And I lose class information. I can't reconstruct the same object identically unless I have it. Now, when you see how this works, I'm going to do an emission, and it creates a photon string. So if I actually look at this emission, it's going to look a little different than what you're used to. This is the photon string. It has all the values. Somewhere in here is Bob and New York.
So that's basically ends up being the raw condensed code that is actually being sent and interpreted.
Right. And it's sent via photons. You can think of this as, in a biological point, you can think of this as the DNA that reconstructs an address record and all the class information, everything that's in there. And when you look at this string, you'll see how compressed it is compared to how much it's bringing back and how much information it's recreating. But so I emitted this string and I sent it to the other machine as a post. Later with my server, there'll be better ways of even transmitting. On the other machine, this represents the other machine. I'm going to materialize this emission. So let me step over it. I now have a clone, which I'm going to cast back to an address record. And I'm going to compare the content. I'm going to get let's say the name and, the restored one, the original one, and compare it and see if they're equal. And in fact, they are. And if you look at how much got transmitted, there's a lot going on inside the atoms. But all this was reproduced. You have an address record and you have the clone. It's all reproduced.
So basically from that 2.5 lines of code, you got out all that.
I got all that, transmitted it. I don't need any tools to serialize this. I don't need any tools to deserialize it. And I'm carrying information that JSON doesn't carry unless you specifically add it in and do some contortions to do that. This is actually reconstructing the class itself. And this will work interlanguage. If you have, I don't have a Java version of it, but the interface would work the same, because I could take a Kotlin address row, transmit it to the other side, and deserialize it on the other side, and have another address row in Java or TypeScript whenever we implement this. And later I'll get into how the mechanisms work and how it actually does that. But you can pretty much see this as a way of super condensed transmission, no work. The downside, as I mentioned before, this is incompatible with everything, because if I actually did use a JSON converter that would serialize to JSON, I can't imagine how big the JSON would be, considering there's all this stuff, time and charge and mass, and within those there's other things, fields. It would.
So in order to try to convert it, you're kind of losing the essence of the whole virtual physics, in that its primary superpower, to my knowledge, is its condensed stability there, because it doesn't require all these outside dependencies, and to build all those dependencies would be a pain in the butt. But if we have that efficiency, if we can do all the stuff, if we can build, basically at least replicate what we have, and it's doing it in a much more effective manner. I mean, if you need to increase the effectiveness of programs and you're already down to the atom, sounds like a pretty good option.
It becomes really powerful. And one of the advantages that virtual physics has that none of the other tools have is I am making an assumption about what's on the other side. I'm saying that all programs are governed by the laws of physics, are using virtual physics. So therefore, I can emit this string and know that it can be interpreted on the other side. If I'm using Angular in my browser and a Spring Boot server on the server, and I don't even know what's there, I'm just going to serialize it in JSON, and here's the actual data fields, and you construct an object in any format that you want. I don't know what's running on the other side. I have no control on it. So one of the differences with virtual physics is that for this to work, there's one law of universe. So you're running virtual physics on the server and you're running virtual physics on the client, and they have the same objects on both sides, and they're all built out of the same things. And I'll talk about that a little bit more as we go forward, but that is one of the superpowers, the fact that we're using the same stuff on both sides. So that's why I can do so much with so little, because there's some basic assumptions. We're all governed by the same laws. And that's what makes pretty much a lot of the superpowers that you're going to see come from the mere fact that we're using virtual physics. And so now on the other side, we can materialize this. The only thing is I left provisions for us to be able to have different languages. I think that's pretty valid. We can have, we can talk about the laws of physics in different languages, but the stuff it's made out of should still behave the same way. Whether I'm speaking French or English, it's still the same laws of physics. So that's the approach that this is taken. So this is one of the first superpowers. Let me get rid of that breakpoint, and and I'll talk about the complexity, because one of the first things, you almost don't know how to debug it, because you have so much stuff. You have atoms and protons and neutrons and electrons and quarks and down to gluons and things. So where is my data? And when you're inside the debugger, how do you find your data? Eventually it's stored in some wavelength of some field somewhere. It's not easy to do. So if you notice things with an underscore, right now I'm using that as a breadcrumb. The things that you're most likely to be interested in are named with an underscore. So they kind of stand out. And, you have a list, there's a memory block. Here's the item name, address, city, state, zip. You go in here, you go into the name. Okay, memory block name. I want to go into the nucleons, protons. There's a value proton. I'll talk about that a little later. You go down to the quark. And then within the quark, it's stored in the wavelength field.
Wait. Echelon. Just looking at this cursorily as a dude on the internet, this looks like a lot like the standard model of particle physics.
Yes, and that's another thing. Like if you take, for example, proton. Let me take a class and look up proton. A proton is a baryon, right? That's the way it is in physics. And within the baryon, let me go down to proton and neutron. Here is, I put them, my methods are all in alphabetical order, so.
Always helpful.
Always helpful, but where did I break with that? Here, I think and then I put private after public. So if we look at a neutron, it has an up and 2 down quarks, and a proton has a down and 2 ups. And I put a lot of the documentation is actually in physics itself. So let me go back to the actual proton. If you want to see how it works, like I said that a proton is a baryon that has 1 down and 2 ups. So if we go here to the proton and we go to the documentation proton, and let me go to the browser. You will see that it has 1 down and 2 up quarks, and there's a description. Each of these quarks, there's some universal properties that all particles have, which is wavelength. They have the 5 dimensions. They have
time, length, charge, mass, temperature.
Temperature, and so on. They also have angular momentum, they have spin, and they have wavelength. And with that information, you can pretty much define everything. And I'll get it. Actually, this is probably a good time to look at some of the code. But the point that I was making is that when you're learning virtual physics, you're also learning physics. And
it's a beautiful thing. It's a beautiful, just looking within the code. It's like, what's the documentation for this? It's like Wikipedia, baryon, proton, and it's like, what? I can try to start to understand what that means, and just that reciprocity there, reciprocity there is a beautiful thing. And just in my opinion, I'm pretty sure that the closer and more effective this gets, this can actually give us hints for what's actually going on in physics itself. We've already had a couple of those insights, and hey, we'll see how it pans out, but it's looking pretty good.
Yeah, and I'd rather, as a new developer, I don't want to learn a page of esoteric stuff about how angular works. I'd rather actually read about a proton because I'm learning something that's useful, even outside of virtual physics. If I'm a chemical engineer, maybe something I just read here is actually useful to me as a chemical engineer. If I'm a nuclear engineer and I'm doing programming, I'm bringing a lot of, especially people who are nuclear engineers, they're bringing a tremendous amount of their knowledge over. A lot of these things are going to be familiar. We have to remember that the behavior of a proton in virtual physics is as close an interpretation to the patterns that are here. It doesn't mean it's a perfect interpretation. Some things are really difficult to interpret. Values are stored in wavelengths because I interpret wavelengths have an infinite range of values. They can be from very low to very high. It's a very useful place to store a number as a value is in the wavelength. The spatial dimension, one of the dimensions space I use for pointers because programs do have space in the sense that when you take a program and you have objects that point to each other, you're creating dimensions. Things become kind of 3D as this points to that and this points to that. That's an interpretation, but it's the closest interpretation to using the laws of physics and the dimensions that we have in programming in the virtual world. So, as time goes by and people work on that, I'm sure people will come up with better interpretations than what I came with. With this, the number one goal of this is to prove the concept that yes, we can use the patterns in physics, we can interpret them. It doesn't mean my interpretations are the best, that they're right. I'm not arguing that. I think they're very good from many, many years of doing this, but as people get involved with it, I'm sure we can get closer and closer interpretations to the way physics actually works and what we interpret that to mean in the virtual world. It's a never-ending tough thing, but I kept doing this over and over again for 22 years because I was never happy. I'll talk about why I think that I got it right and what I did wrong that made me have to do it over and over again every 4 and 5 years. Is, when I first started, I only went down to the atoms. I didn't have protons, I didn't have neutrons, gluons, all that other stuff. It just wasn't there. I created atoms, and then I created my own virtual atom and invented some behaviors that wasn't physics. And it worked pretty good, and I did a lot of things, but things would start falling apart. But the things that were bad in my code were the things that I invented. Whenever I used my creativity, invented my own particles and behavior, as I built and layered on top of it, those were the things that broke first. So then I'd scrap it all and I'd start all over and say, well, atoms have protons. Let me use the real particle, not my creation of a particle. And it got better. And a lot of times, as I build on, it would fall apart. And then I'd find out, God, the weaknesses of the things that I invented, the things that the patterns that are there in physics just seem to work. They just seem to work. And the change that I made also when I switched to Kotlin is I became adamant after probably 18 years of doing this over and over again and realizing everything that was wrong with every approach I took was my own making. It was the stuff that I used my creativity to think I'm smarter than the universe. So I became adamant that I will only interpret what's there to the best of my ability. And then a lot of the superpowers came out of this, and you'll see some more. That's just one of them, the way this can emit and absorb with ease. And all of a sudden, I feel like I have a really good interpretation of the laws of physics because I didn't introduce my own particles into the universe. And so when you look at this, when we're trying, let me go back to the radiation.
Well, just that observation in and of itself, it's like by adhering to the laws of reality as we know them, things just run more efficiently. And it took decades to figure that out. That observation in and of itself is so powerful. And it's also one of those things where apparently you've already blown up Cycle's mind. They're like, whoa, mind blown right there. But it's a beautiful thing and it makes sense.
Yeah, the hardest thing to learn is to ignore yourself. And that's why, this is kind of interesting here. I have a hunch that this paradigm, virtual physics, can provide additional insights into exotic states of matter like Bose-Einstein condensates and BECs. I don't know what BECs are. But,
BEC is just short for Bose-Einsteinian condensate. Same thing. It's short.
Okay. BECs. Okay. Yes, and actually, Matthew and I have had several discussions during the development of this that, Matthew and Thad have been doing a lot of work on the math, looking at the laws of physics from a mathematical point of view. I've been looking at it, from the standard model, from the data points. I can say every particle has these data points. So this is the information that the universe is carrying. And therefore, that should be enough. And one thing, when we go into the atoms, let me go into like this atom here has multiple protons. And I've noticed, later we'll see how I build it into molecules. I do not need to add any more data because if you have a molecule and you have multiple fields like name, address, city, state, zip, that becomes a molecule or a compound. Each atom has enough information between the 5 dimensions, angular momentum, spin, and wavelength that you carry enough information in each of these particles that if you group them together, you never need to create a new field that's not based on an atom. And the fact that I can now do that, that everything derives from that, which means everything is transmittable. If you wonder, how do we do this emission? How do we know how to emit it? Well, the address record itself, let me go into that. It extends compound. And I'm using a lot of kind of multiple inheritance with mix-ins, which I'll cover that in a different segment, without going too deep. But if you look at the fields, the way it works is I'm adding name, address, city, state, zip as atoms on this compound. And, compound extends molecular and so on. And every atom has multiple fields. And we'll talk about it. Not only, I haven't put this in this version, but it's coming very soon. I can store all the metadata, field names, colors, like whatever I want associated with this. And I'll talk a little bit about the dictionary approach to this. But tremendous amount of information can be transmitted in an atom, and it carries all of its own self-defining information. So now we group these together into a compound, and the address record really extends compound and just bundles the things together that we want to bundle. And then boom, it can be transmitted and absorbed, because physics understands atoms. Physics understands protons. It already knows how to do it. So that's one of the magical superpowers that allows this to be able to emit and absorb so easily, is the fact that it's all based on physics. And let me go and show some other superpowers. I want to cover some electronics.
So I realize some folks that may be watching now maybe don't have really like a history, but basically what Eschelon is showing is basically something that he helped me with right as we were starting here. So basically, if you want to grab any of this stuff here and just start to play around, what you would do is you would go down to basically either physicsmonastery.earth and go to the virtual physics tab, or just search GitHub for virtual physics. You'll see Eschelon's repository right here, and you can download it. As you can see, we got our README here. Basically, I mean, the concept, it seems to make so much sense. And when I learned that Wolfram, one of their base units is the atom itself, because I think he had similar intuition. And again, he also had the company to do and everything, so he couldn't just be like, all right, so let's break these down into quarks. And even he's admitted that, well, some of the things for the language over the past 35 years to keep it coherent, there's been hacks in it and everything. And those are things that I feel at some point he does want to address. But if you want any of the code here, basically you would just go over here, you click copy there. You would need to download something like IntelliJ to basically run this, because this happens to be a Kotlin library here. That happens to be the language that this is in there. So then you would go over there, and then you would go into something like, have this guy right here. This is an IntelliJ terminal. You can just get this from JetBrains. But basically, this is where Eschelon is right now. He's just in here. I happen to have my project. You would just open up a terminal, you code yourself the little thing. There's probably Ask ChatGPT, could help you there. Or if you happen to know some, I would claim, genius programmer like Eschelon, maybe he could run you through it. But I at least have this installed, and I can hopefully start to play around with it a little bit after this. But we'll get back to the Eschelon's presentation. Sorry, sir.
Okay, no, that was good, because people need to know where to get it.
Mm-hmm.
Here, let me go to a conductor. Let me start with conductors. You have atom 1 and atom 2. And what we're doing is we're saying, atom 1 is being initialized to whatever's here, atom 1. Let me scroll up. Yeah, atom 1 is atom 1, atom 2, atom 3. And then atom 1 new is atom 1 new, and atom 3 new is atom 3 new. So it's very simple. What you see is what you get. So what I'm saying here, when we're in a conductor, I'm setting atom 1 as a conductor to atom 2 and atom 3. So what this is saying is, if atom 3 changes, all three of these values change together. If atom 1 changes, it flows upstream, and atom 3 changes. So these are all bound together. I have a little description what the underscore means is there's different ways we can chain them. So this underscore points to the value that's being returned from the conductor. So atom 1 conducts to atom 2. I'm pointing to atom 2, so that becomes atom 2 dot conductor atom 3. When there's no underscore, we're at the end. But if I put the underscore on this side instead of that side, it actually has a different semantic meaning. What it's saying is that atom 1 and atom 2 are conductors, and then atom 1 is being returned, and atom 1 and atom 3 are being conductors. Now, in the case of conductors, it doesn't really matter because it's going to flow between all of them anyway. But when we get into diodes, which are one-way conductors, right here.
So you're basically explaining the data flow process.
The data flow process. The diode, you can think of it in like in electronics, is a one-way gate, so that electricity flows one way. So in this case, if I started off atom 1, atom 2, atom 3 with different values. When I change atom 2, it's going to change atom 1, but not atom 3 because that's upstream. If I change atom 3, all of these in a row are going to change. If I had put the underscore here like this, now what we're really saying is atom 3 is dioded to atom 1 and atom 2 is dioded to atom 1. It's more of a tree. So if atom 3 changes, atom 1 will change. If atom 2 changes, atom 1 will change. But atom 3 and atom 2 will have no effect on each other. So that's kind of how you read it. The underscore is pointing to the atom that's being returned for the next step in the chain. So you can think of it as a pointer. So this is kind of a superpower that comes in it. If we step through some of this stuff, the way it works is, I have a diode relationship, and let's go to the diode. I'm getting like the current proton, the proton value of here. Now, briefly, let me describe how values are stored because it's important. You have protons and electrons, which actually have the current value. Values are stored within the protons in the down quark of the proton. And I'll come back to what the other quarks are used for, and I'm still interpreting some of them. But the down quark has the value. Neutrons are kind of interesting, and maybe I'll get to that. Let me show another superpower, and it'll make more sense. Let me back up a little. Let me go into nuclear, and then I'll talk about the structure. One of the things, I have an atom. It has atom 1, and I can either set the value to new stuff, which is fine. It has a new value, great. But if I want to save the previous value, I can do a beta plus decay. A beta plus decay decays a proton into a neutron. The neutron attaches itself to the atom and stores the previous version. As in physics in the real world, the atom just got heavier because now we have a neutron. And in the virtual world, the atom got heavier. We have an extra neutron with the previous value. And we can see, but if we go, we can see the value did change, but if I do beta minus decay, it's returning the neutron back to the proton. And the proton basically, this ran backwards. I basically did the equivalent of a database rollback. So now I can take these properties and put that in whole molecules. Like here's our address record. I did a beta plus decay, which converted all the atoms. Now they all are heavier. They all have neutrons. I can set name to, address to, state to, whatever I want, and print it out, and you'll see that it changed. And then let's say I'm on a web form where they have a reset button. Oh, change my mind. I screwed that up. They click reset. Normally in programming, you'd have to create a before and after image. They hit reset. You take the after image and copy it all back to the previous image and do all this stuff. In this case, I'll go row beta minus decay and print it, and everything got rolled back. So it's very helpful.
So is this operating as a form of like a cache, or?
Yeah, kind of.
I realize I'm taking it from a client side internet perspective right now, but a lot of times if I'm like, all right, this data will use cookies and stuff like that. So you click on that thing, so it'll have something stored there, so it might make the web form easier to operate. Is it something akin to that, or a bit different, or?
It's not so much for the user, it's for the programmer to enable this for the user, so that, you know, if as a programmer using, you know, whatever, you name your tool, Angular, React, I have a web form. And if the requirements are like, this is a complicated web form where they have a lot of information, and they might want to have a reset button to start over. Maybe they change their mind, or they read down on the form and it says, oh, you know, like it says only use this form if you're over 18 and you're 17. So you hit reset because it doesn't apply to you. As a programmer, you know, if I give them a reset option, I have to take a snapshot of the form and put it aside with all the previous values, let them change all the current values. Then they hit reset and I have to copy everything back and then get rid of it and, you know, reinitialize things. This makes it really simple. They hit the reset button. I say main beta minus decay, and the address record or the entire contents of the form roll back. So as a programmer, my life just became really easy, because if I want this to be able to be rolled back, I just execute beta plus decay and it creates neutrons for every proton on this atom. And beta minus decay reverses the decay of the neutrons back into the proton position, and the values come back. So this is a superpower, and the reason this superpower works really well, it was a question of interpreting. I wanted this capability. Where would that be in the laws of physics? If we have chemistry and we have atoms, and and the values are stored ultimately in the wavelength of the quarks, where would I store previous values? And it's like, well, if I'm storing previous values, it's getting heavier, but it doesn't interact like when you're using diodes and conductors and electrons, or if you're using chemistry, and I'll show some rudimentary
The data doesn't flow as in the other ways that we're kind of used to. It's doing something else.
Right. It's basically dead weight that doesn't interfere with anything. So where have I seen dead weight that doesn't interfere with anything before? And it's like, isotopes. Neutrons are dead weight that don't interfere with the chemical reaction or behavior of things.
The neutrons may disagree with you, but yes, it's the non-interacting additional mass. Yeah.
Right. So it's a question of interpreting that and finding
different interacting. I should clarify. I'm sorry. I want to be precise. Sorry.
But chemically, it's the same interaction.
Yeah, there's no charge there. For chemistry, it's like, oh, there's just a different shape.
It's just a different shape, more neutrons, extra weight. So, and coincidentally, neutrons are made of the same quark. So it's very easy to take, oh, well, I have a value quark. I have a down quark and a proton. Oh, guess what? I happen to have a down quark and a neutron. That seems like a pretty good thing to map. That now I have dead weight in a neutron that exactly matches the structure that I already have for the values. So that's where it went. And a lot of the struggle over the years, one of the problems that I ran into with the very first version is, you know, I tried to make the original physics as authentic to the laws of physics as I can get it with the limited knowledge I had at the time. And, you know, but it's kind of like building an F-16 fighter in your garage. Like, even if you do it perfect, it doesn't mean you know how to fly. And that was the problem I had. It's like, all right, I have all these simulated neutrons, well, at that time I didn't have neutrons and protons, but it was atoms and molecules and all that, you know, gravity. I had some of that. How do I use this? How do I write a program? And my interpretations were pretty off and pretty wild. And, you know, when do you use photons? I think now I have photons down pat. Photons are actually the emission string. What you saw is the most compact form. It's timeless. The photon stream is at the speed of light, time stops. And when you emit from one machine into the other, you're not governed by the clock of either machine. So it really looks, the most compact string that has no time seems like where I'd want to do the communication between two things. And coincidentally, we use radio waves and things to communicate. So it's been kind of years interpreting physics, and the more people that gets involved in it, the better interpretations we're going to get, the closer this is going to get. And I think that's really exciting thing to see. But now here we have these atoms, and they can we can modify them and roll them back. Let me introduce us to, let's see, we did chemistry, we did some radiation, we did some electronics. We didn't do chemistry. And this is kind of rudimentary. I'm going to add to it. In prior versions of this that were written in Java, I got a lot further. I had, pretty powerful catalysts. But here, I'm creating I'm creating a polymer. Now, for those that don't know chemistry, polymers are repeating strings of molecules. If you look at an address row, this is a molecule or a compound, right? We look at it, extends compound. Let me go back to chemistry. So these are repeating rows, like, some plastics crystals, like, there's a lot of things that basically take on the polymer form. So I'm binding these molecules to a polymer. Now, when
we did have a question. Upcycle is wondering, have you written a Quine, a self-replicating program that outputs its own code without any input? One example of a self-replicating structure is found in certain types of crystals.
I haven't tried that. I'm fully sure. Let's see. In self-replicating product outputs its own code. In a sense, this does, and I'll explain. One example: self-replicating structure found in.
I just learned a new word. I didn't even. When I heard Quine, I think about like Thomas Quine and like philosophy and stuff. But Quine, it takes no input. It produces a copy of its own source code. It's its only output. That's okay. I'm sorry. Continue, sir.
Yeah, what you're seeing here is we now have a chemical composition, kind of like a crystal. It's a polymer. And I want to filter only name 2 and city name 2. So I'm creating a filter. And a filter, if we remember the definition of a catalyst, it extends catalysts. Catalysts are chemical compounds that interact with other compounds but don't interfere and inject themselves into it, but are transformative. So in this case, a filter is a kind of catalyst. So when we run this, I'm creating a filter where, and here's the atom, name 2, and where city is city 2, and I'm activating the catalyst, and what I'm getting back on, result size is 1 row. It's getting back this row. And, right now it's rudimentary because I'm rebuilding stuff that took years of work that I built on top of prior versions that I wasn't happy with. And I'm rebuilding a lot of my old code, rebuilding it on top of the new virtual physics because I'm way more happy with this.
Work.
But we can have where and, not all that other stuff I'm going to add to this. But now we have a built-in query language. We can basically take our compounds or molecules and bind them into polymers, and then we can query it using catalysts. And so now we have rudimentary chemistry going on. The mere fact that these are atoms that are built inside of compounds and molecules, the query itself can make certain assumptions, just like we can transmit data from one machine to another, because we have some very powerful assumptions. We know they're running virtual physics on the other side. We know they can understand this emission string. Well, the same thing, because we're doing chemistry and we assume that everything that we're operating on is an atom that has a proton, that has a value. It could even have neutrons in it if the catalyst wants to roll, do an automatic rollback itself inside the catalyst. It knows how to do that because it understands the data that it's dealing with. So in a sense, by searching for the unified field theory of programming, we have a foundation that everything can depend on, which is the way it works in the real world. And
I know I find Upcycle recommends that might actually be an interesting little experiment to to see what
Yeah.
happens mucking around with the clients. But continue. So we're going on for a little bit over an hour, maybe just this and maybe one more superpower.
Okay, well, there's another superpower coming. I covered the ones that are here. What's coming is, and let me talk about the dictionary way of building. In my test cases, I have a dictionary of atoms and composites, because we want to think about the projects like address extends atom, capacitor. I didn't even get into the capacitors yet. I will cover that really quickly. I'm creating this dictionary of all these things, so anyone who's building applications, whether it's client or server side, they want to use the same dictionary. They want to use this address for address. One of the superpowers that's coming is it's going to be very easy to add properties. So you can attach to the atom, for example, the alias name for address. So if I have net amount, the alias name is going to be NET AMT as opposed to NET amount. And that'll be universal on all your screens. If you export to spreadsheets and make CSV files, it's defined actually in the dictionary as the metadata for each of these atoms. You can have multiple protons. The interpretation of protons in the sense of atoms is, normally we think of it as new elements, hydrogen, helium, and going, all the way up. In this case, metadata, as you add metadata, it becomes kind of a different atom, and it has more values in the protons. You can define, I can hard code that city will always be red. So when you're in the browser and you want to display this on the screen, you take the color that came with the city. We universally define that city always has a red background. Probably doesn't make sense to do that, but if that's what we define, we can go and tweak the dictionary, change the color to blue. And when we recompile, everywhere in the universe, city, now part of the dictionary, is always displayed in green and is spelled CITY. So those things are coming really quickly with this resistor. When I showed you the diode, there may be cases where we don't want to accept the change for whatever reason. That's another thing that's coming. One of the superpowers is all of the constraints are going to be inside the atom. So for example, if I define a zip code, then it must be numeric 5 digits, but not below a certain number, not greater than a certain number. We can reject the change. So if we look inside of the code itself, let me go to the test case so you can see how I'm using that. Let me go here, electronics. For one of these atoms, somewhere in here, I used a resistor. Here, I'm setting the content. I set up this diode relationship. You can trap a tau anti-tau pair that comes back. It's a lepton pair. The tau has the current value, the anti-tau has the previous value. The reason I interpret anti-taus as the previous version, it's kind of antimatter that we can use. It's another way that I can reset the value. And I can also look at the anti-tau and see information as to why it failed. I can pass back a reason code. So if I'm chaining these things together in diodes in my program and the electrons flow, and for some reason atom 1 is tied to the database and can do a more thorough evaluation and says there's no such city, it can actually respond and send messages back up the chain the other way. And I can actually see, not only did the value not get set, but I can see the reason why. Let me get rid of this one. Here, if I look in that pair, pair 1, let me go into,
well, that's all the stuff in there.
Yeah, it has the current one. Let me go to its parent. Or is it on the second one? Set content atom new to atom 1. Which one is the resistor? Atom 1 is the resistor.
Welcome to live internet, everybody. No one was asking a question that I think I have an answer to, and the answer is we haven't tried, and I don't think we're there yet. The question is, old idea. If the sun can have a little black hole inside, have we tried virtual simulations on that idea?
I haven't. The trying to interpret black holes in a sense of what does that mean to programming? Where does black holes exist in programming? And I've that one's kind of a gray issue. It's between a database and a neutron star. The reason I'm leaning towards, and this is, I'm definitely open for ideas, but a neutron star reminds me of a database because it's nothing but neutrons. It's nothing but values. There's nothing active. There's nothing flowing. It's just kind of dead weight. So if you take the metaphor of the neutrons carry prior values, that's kind of the state that goes in there. Some of the argument, for black hole, I don't think it's, black hole doesn't sound like a database to me, but the neutron star does. So if we look into nature, where do databases exist? It seems like a neutron star is a perfect example. You have, let's say, a database of just rows and columns of compressed data. It seems to fit, you'd read that in, and those would be, and you create like an address record, reverse decay it, and now they become the proton values, and off you go. I don't think this library, we've talked about the idea of having a virtual simulator. Like if you look at, we have CERN, costs billions of dollars to build, and we smash particles together at nearly the speed of light head on. And that's all we can do. Well, if someday, hopefully with some of the math and, that Matthew and Thad are now working on, and Matthew's learning a lot about his work. If we can figure out how to simulate physics and then use virtual physics to build a simulator, now we can smash particles at 90-degree angles or 35-degree angles, and one at almost the speed of light and one at 100 miles an hour. And then
see what happens.
Mathematics and see what happens. And now we can build all these virtual simulators.
The funny thing, I'm sorry, I'm totally pitching Professor Kerr's paper again, but you said another thing. That's his whole thing about saying, he's like, well, why does it have to be a singularity? People are basically just saying this because Professor Penrose was like, well, this seems evident. And even when Professor Penrose got his Nobel Prize, they said something about ultra-dense bodies. They never used the term singularity. And this paper, he's talking about like what happens. He's like, most probably all believe that this standard model is non-singular for neutron stars, but not for black holes. He's like, why the difference? The actual density can be even lower for very large, fast-rotating black hole interior. Because his whole thing is, he gets a ring singularity, but he's like, that's supposed to be the physical interpretation is, there's just a super dense star in there. That's all he's saying. He's not trying to say, like, there's some infinity here that we can't explain. He's like, well, if a neutron star is dense enough and it's rotating fast enough, you'll eventually get an event horizon anyway. So that's kind of his claim, which it sounded like what you were saying. It just reminded me of the paper again. So
true. So it's black holes. I haven't found a use to map it in virtual physics yet. I don't know where it belongs. I've also spent time saying, well, black holes might be outside of our universe, like our break in the universe. So I've experimented with, you'll see in the virtual physics library, there is black hole and event horizon. I think I'm leaning towards the event horizon as a way to interface with the outside world of other software so that virtual physics is not totally incompatible with the entire virtual world that we've already created. I can probably say like some APIs exist in a black hole and you interface through them through the event horizon and have some way to communicate with other software short of having to rebuild everything. So that's kind of an idea. But very quickly, I actually am in the breakpoint, accepted reason code. If we look at this, accepted is false. reason is nope. If you looked at, when I rejected it, and the reason code is a value 20. So these atoms could be arranged in diodes or conductors or capacitors. I'll probably come to capacitors in another time. A capacitor doesn't actually transmit the value. It just notifies the other atom that a state changed. Where that comes in handy is I've done a lot of 2D graphics. We have one box or rectangle containing another box. And let's say the inner box has a length of 100. The outer box is twice the size, 200. Well, I don't want, if I resize the inside, I don't want the outside to be the same. I want it to be twice as much, whatever this changed. So I can set up a capacitor relationship so that this value notifies the other value. I'm now 200. So it says, oh, let me multiply that by 2. I'm 400, and the outer box gets twice as big. So
I think you, whether you know it or not, actually created a programming gauge theory right there. Because that's basically, you're changing the thing. Because the way Dr. Weinstein had explained it, he's like, all right, so if you're on Mount Everest, how high are you? It's like, well, in comparison to what? We often do sea level. So you're at like, what, 29,000 something feet or whatever it is there on Mount Everest. It's like, well, what if it's the bottom of the ocean floor? What if it was the average height in Tibet there? It's like, your actual height will vary depending on the gauge reference frame you're looking at, right? So.
Yeah, or we could say we're 29,000 feet below Mount Everest,
Yeah, exactly. I like that. Yeah, perfect.
So there's more superpowers to come that are just kind of built in. And I can't take credit. I didn't design this with these superpowers in mind, which makes it pretty spectacular. It's things that just happened. As I was building this, I'd be like, well, how am I going to transmit it? And I'd look at it and say, wait a minute, this is almost self-transmitting already. And like, wow. And how do I, link atoms together and do diodes? And it's, well, I have the electrons, and, if you step through the code, you can see how it works. And it's like 90% of it was already there. So that's what made me keep going. As many times as I failed and got my interpretations wrong, I kept noticing that the closer I got to the laws of physics and the more authentic it became, the more powerful this library became. So the real insight is to realizing, is to get rid of myself, take myself out of it, and just use what's there and trust in the patterns that exist in nature. And, with that, there's a lot more that I can talk about, but I think this probably does make a pretty good intro. Things that you can use it for and things that you can't. This is probably important. I think right now, all of us should probably, download it and learn from it, get ideas. It's really missing the server because there's two things that I'm going to be working on, is creating a new web library that's based on virtual physics. That would be kind of a replacement for Angular and React. And the server that's there is a real-time WebSocket server that we can do in another video why it's that way. But it's, this is definitely good enough to start experimenting with, to learn it. Actually learn some physics while you're at it, because the more you have the standard model in your head, the more this starts to make sense, and the easier it is to understand the code. Another thing that I definitely have to do, and I promise I'll work on it, is this is a little hard to debug because there's so much stuff going on. Like when you look at this, you look in here and you try to debug. Well, I'm not in the debugger. Let me go back here. When you look inside the debugger, it could almost be overwhelming, the amount of information that's inside of the atoms.
It's because it's all compressed.
It's so compressed. And so there's some improvements. I have a lot of ideas, but some improvements that'll make it a little easier to debug. But most of it I'm pretty happy with. And, the more people that work on it, the closer we can get it to physics, the more powerful I could swear this is going to be, because I've done it for 22 years. And the closer it gets to physics, the more powerful it turns out to be. So, with that being said, I guess this is a pretty good intro to the code. Definitely going to do some more videos, and
okay.
I don't know.
No, that was great. You went over. Did I understand everything you said? No, but I'm starting to follow the logic. It's to the point where it's like, oh my God, I have this downloaded and installed. I'm going to have to muck around with it. And of course, I'm going to make a heck of a lot of mistakes, but at least just taking just what I've learned over the past few years about like physics and everything, maybe see it's like, okay, well, I guess this would make sense and just see what we can come up with. And it's like I said, the more folks that kind of start playing around, seeing what they can do and everything, the faster we can just mimetically get it out there. Be like, hey, here's an option here. And once we actually get some, maybe some old school and even a lot of young folks and everything that start playing around and are like, oh, what happens if I do this? It's like, it'll start catching on. And was it, you had released this like within the past week, about a week or so, and it's been downloaded how many times so far?
Yeah, like almost 200 times. So I don't know what people are doing with it, but people are looking at it. And there's a few things that one of the goals that I have, if you can use your imagination, where I'm trying to get, it's going to take a while, but let me go back to this is going to be a revolutionary and radical new way of thinking about internet communication. But you see, we have these diodes and conductors. Mm-hmm. Just imagine if Atom 2 is actually on the other machine, the address record on the other machine. So now you make a change.
Oh, now we're getting into entanglement and everything there.
Exactly.
Beautiful.
In fact, I called it entanglement. They become entangled, and then you get notified when the value changed. Every atom has a value change notification, so you can actually take action. But now you're not even dealing with the emissions. The values are actually dynamically changing, and you're getting notification. You can edit it right there and save it into the database. That's where I'm trying to get to. That's one of the reasons the server is a real-time server using web sockets, because in order to do that, you have to be real-time connected. The server is really, really fast. And so it's not going to be a general purpose server. It's not going to replace Apache, or that's not its goal. Its goal is to start everything new, and we're going to have to rethink how to even program like this, because you know, when you have inter-machine diodes, how do you break the problem down and solve how do you think like that? And that's been an ongoing problem that I've had with this library from the beginning, is like, you know, when do I use a neutron? Like, how do I think like this? And it's been an incredible learning curve. Now, the goal is to spread this to distributed computing and using physics and relearning how do I think and break problems down using this new metaphor, not fall into old ways of doing things. And that, I think, is going to be a learning curve for me and the community as we bend our mind around it. And so I think it's at that exciting phase where, you know, definitely look through the code. It's fun to step through. It's fun to see actually physics running. You're seeing electrons and protons and neutrons and quarks, and, you know, there's no fake particles. One other quick thing, I keep saying that. In order to do emissions, you have the standard library, but address and address row are not part of physics. You have to build that. You create, on startup of every application, the first thing you do is initialize the absorber. If you don't specify anything here, if you don't specify that, you're only using, you know, protons, you know, atoms and the things that are built into physics. But in real life, you have your own stuff you want to transmit. So you're going to create your own emitter class that extends class group. And you basically, you know, you create a class ID and the type. And that gets added to the list of physics. And now address and address row and all these things can be transmitted machine to machine.
So how you would have your normal setup for a number of different web pages and stuff.
Right. This is kind of like a registry of the things that you want to be able to transmit.
Cool.
So I think I kind of covered very surfacey, you know, the concepts behind virtual physics.
No, because my thing is like, well, how would you build in the actual things? Are you going to call it protons? Like, no, you just do it here, and then it will do all its things, and you have it assigned, and like, oh, if I had more of a rudimentary background on programming, I probably would have already understood that. But now at this point, I seem to start to be understanding it. So, thank you.
Yeah, And if you already know physics and you learn the standard model of physics, so much stuff will be familiar, and you'll kind of know what to expect. So
Cool.
definitely, bridge the gap.
All right. So, wow, we nailed it right at like an hour and a half right there. That was beautiful. It's we went over all the stuff. So, Echelon, hey, thank you so much, my friend, for coming on, helping walk me and the other folks through and everything. And we'll take some snippets and help to explain it more. We'll do a few more of these over the next couple of weeks. So, other than that, peace out, everybody. Take care of yourselves. It's a crazy world out there, but hey, I think a new door is open in 2024.